Okay. Okay, I'm back here again. And this time I'm going to be looking at the basic gas laws. I'm not doing any problem solving. I just want to talk about the gas laws in principle. Later on I'll see about maybe doing some examples or two, but that would be in another video. Okay, well, what about the gas laws? Well, certainly it's a big thing in chemistry. And when we look at the gas laws, there's three things you got to look at. You have to look at the pressure, you have to look at temperature, and you have to look at the volume. So those are your three main things. Now we do have the ideal gas law, but I'm going to talk about that toward the end of the video. So the first one we want to look at is the really, really basic one. It was done by an Englishman, Sir Robert Boyle. He experimented with gas, and we call it Boyle's law. Notice it's not a theory. And the idea was that if he kept the temperature the same, then the pressure times the volume is going to equal some constant K, which seems to hold true for no matter what the condition may be, except that the temperature has to be the same. That's a big thing. So when we look at this, we have a beginning and we have an end when we look at these formulas. So when you see P1, V1, you could say the pressure at the start times the volume at the start is equal to P2, V2, or the pressure at the end times the volume at the end. And that's a pretty key thing. Now notice there's no temperature here. That's because we're keeping it constant. If the temperature is not constant, then this formula is just not valid. And then we need to find something else. Okay, so the idea about this is that P times V is equal to some constant K. It doesn't matter if it's at the beginning, or it's at the end, or it's at the middle. Doesn't matter. Okay, but what we do know about pressure and volume is this. If the pressure goes up, the volume goes down. If the pressure goes down, the volume goes up. This is an inverse relationship, inversely proportional relationship, like this. Okay, pressure go down, volume go up. Pressure go up, volume go down. It's that simple. Okay, all right, let's move on. The next one was Charle's law. Charles was a French chemist, and he too messed around with the gases. And what he found was that the volume is equal to some constant K multiplied by T if the temperature is in Kelvin. Now, the key thing about this is, well, why wouldn't we do this in Celsius? Because that's the metric thing. But you have to understand, when you're working with some of these equations, you cannot have a negative Celsius or a Celsius below the freezing point of water. It's, well, why not? That would mess up the math calculations. Well, what's going on here? Well, when the French Revolution happened, they set up a new temperature system, and that's where the Celsius was created. And they decided that the freezing point would be set at 0, which was the freezing point of water. So there are gases out there that they're still gases even though they're below the freezing point of water. So that's why they had to come up with another temperature system to add on to it. 1 Kelvin is still 1 degree Celsius on a temperature scale. But to eliminate the negative numbers, what they do is Kelvin is equal to the Celsius plus 273.15. Kelvin, to change the Celsius to Kelvin. It's pretty easy. I've done 273.15 with my students, but I've also done 273, because let's face it, 273 is pretty quick and easy and simple. But in this case, we're looking at Charle's law, and we would need to use Kelvin as our temperature. Now, with Charle's law, it was very important that the pressure were kept constant, because if the pressure is not kept constant, then this law isn't going to work. You need something else. So volume 1 over temperature 1 is equal to volume 2 over temperature 2. That's the key thing about Charle's law. Pressure's the same. So the volume at the beginning divided by the temperature at the beginning is equal to the volume at the end divided by the temperature at the end. That's basically it. Okay? Not too bad. But we need to move on here. Now we have Avogadro's law. Now, Avogadro was credited for coming up with the idea of the mole, the number of the mole. Okay. Now, in this case here, the volume is equal to some constant K multiplied by N, where N is the number of moles of gas. Now, if we keep the temperature and pressure the same, the volume of gas is directly related to the number of moles. So, if we have same temperature, same pressure, here's volume at the beginning, the number of moles we have at the beginning is equal to the volume at the end divided by the number of moles at the end. So if we have 1 liter of gas that has 1 mole in it, okay, it's going to equal 2 liters of gas with 2 moles of gas in it, because the constant is the same. Okay, that's basically it, and I'm not worried about that. I'm not worried too much about Avogadro's. Now we need to look at another law, the Gay-Lussac or Gay-Lussac Law. And in this case here, we are keeping the volume the same. We're keeping the volume constant, whereas the others, we fixed the pressure, we fixed the temperature. Now here we're fixing the volume. This is going to be interesting. So P is equal to some constant K divided by T. So P1 over T1 is equal to P2 divided by T2, or P at the beginning divided by the beginning temperature is equal to the pressure at the end divided by the temperature at the end. That's basically it. So we have a beginning and we have an end here for the Gay-Lussac Law. Now, I'll be honest with you, I couldn't keep track which law belonged to which. So I like this one. This one is very straightforward. It's the combined gas law. If we keep the number of moles of gas the same, we can use this formula and cancel out the other things that don't change. So if we look at it, if we turn around and say, okay, we keep the temperature the same, we have P1 times V1 is equal to P2 times V2, or Boyle's law. Yeah, can you imagine that? Now, on the other hand, if we kept the pressure the same, okay, then we have V1 over T1 is equal to V2 over T2. Guess what? That's Charle's law. Yeah, absolutely. Okay? And if we kept the volume the same, where it's P1 over T1 is equal to P2 over T2, guess what? Gay-Lussac's law. So I don't have to sit there and memorize 3 different laws when the combined gas law will take care of everything. You don't have to necessarily work harder, work smarter. Okay? All right. Now, we need to go on because we have to talk about the ideal gas law. Okay, as I wrap this up. This is the last law I would want to talk about with you guys. Now, the ideal gas law is not the same, obviously, as the others. Because the ideal gas law, we're assuming that the gas would behave in a certain way, a certain fashion, okay? And what this is, it is giving us a snapshot of what the gas is up to now. Think about it that way. It's a snapshot. You take a quick picture, upload it. That's it. That's what the gas is doing, okay? Whereas if you looked at the combined gas law, there's a beginning and an end. Here with this formula, there is no beginning and end. There's just, it is, right now. That's it. Okay, so pressure times volume is equal to N times R times T. Okay, well, in this case, well, what's R? R is a constant. Now, they have found this constant through various methods. We're not interested in that at this point. Excuse me. So, PV equals nRT. So if we want to get a snapshot of a gas at a certain point in time and that's it, that's the formula that we use, okay? Now we do have certain standard conditions, okay, like 1 atmosphere at 0 degrees Celsius, that's standard temperature pressure conditions, STP. And here, if the volume is 22.41 liters at 1 atmosphere, 0 degrees Celsius, where N is equal to 1 mole, what is the constant R? Okay, and notice you have to keep these units intact. All right? Now you can say, but wait a minute. Here's our R constant, liters times atmospheres divided by mole times Kelvin. Well, wait a minute, you got a Celsius here. You're right, but here's the thing. 1 Celsius is equal to 1 Kelvin on the temperature scale. So it really doesn't matter, okay? As long as we add the 273.15 to here, because if we try to divide that by 0, we're going to have some problems with that. So we have to do that. So, ladies and gentlemen, we've covered a bunch of laws here. The ideal gas law, which is the snapshot of the gas at that moment in time. We looked at the idea of the combined gas law, which took into account Boyle's law, keeping the temperature the same. Charle's law, keeping the pressure the same. And then, of course, Gay-Lussac's law, where we keep the volume the same. Instead of memorizing those 3 formulas, just make the combined gas law and you're good to go. That's the beauty of it. Okay, ladies and gentlemen, we're done here. I'll do another video where we'll work on a few gas law problems. Until then, take care. Have a good one.